Take a look at this equation. At first glance, it might seem like just another algebraic puzzle, but there's something beautifully deceptive about its symmetric structure that makes it far more interesting than it appears. We're looking for all positive values of x that satisfy this equation, where a is some constant strictly between 0 and 1. The symmetry here is striking. On one side, we have x raised to this nested power, and on the other side, the roles are completely flipped. Now, before we dive into the heavy lifting, there's a clever observation we can make that will dramatically simplify our search space. Let's think about where solutions could possibly live. Here's the key observation. The left side of our transformed equation is an increasing function of x, while the right side is decreasing. This means they can intersect at most once. When you have these towering exponentials, logarithms are your best friend for bringing everything down to a more manageable level. So we get the natural's log of this towering exponential on the left equals the natural log of the towering exponential on the right. Now here's where that fundamental logarithm property comes to the rescue. The log of something raised to a power equals that power times the log of the base. And this simplifies beautifully using the power rule for logarithms. We get these exponential terms multiplied by their respective logarithms. Now here's where things get interesting. Let's think about the signs of these two sides. Remember, a is between 0 and 1, which means the natural log of a is negative. Suppose x were greater than 1. Then, the natural log of x would be positive. And since the exponential term is always positive, the entire left side would be positive. But wait, is this the only solution? To answer this, we need to dig deeper into the behavior of our transformed equation. Let's see if x can equal anything else. And there's our contradiction: factorial a positive number can't equal a negative number. So any solution must have x between 0 and 1 inclusive. Now, when you see an equation this symmetric, there's often an elegant solution hiding in plain sight. What if we try x equals a? Given our domain restriction, this is certainly a valid candidate worth testing. Beautiful! When we make this substitution, both sides become identical. But here's the million-dollar question. Is this the only solution? To answer that question rigorously, we need a more systematic approach. And sometimes in mathematics, the right substitution can turn a complicated problem into something much more manageable. Let's go back to our logarithmic form. Here's the key insight. Since we know x must be between 0 and 1, and a is also in that range, we can express one in terms of the other using an exponential relationship. So let's make this substitution for some positive value. This will help us transform our problem into something we can analyze more systematically. Now watch what happens when we make this substitution throughout our equation. The equation transforms into this more complex-looking but actually more workable form. Now we can clean this up using those fundamental exponent and logarithm rules we all know and love. The logarithm simplifies using the power rule, and the nested exponential becomes a single exponential with multiplied exponents. Notice that both sides have the same logarithmic factor. Since a isn't equal to 1, this factor is non-zero, so we can safely divide it out. And we're left with this much cleaner equation. Our new variable u multiplied by this exponential tower equals this simpler exponential. Here's another clever move. Let's take the logarithm with a as the base. Even though this base is less than 1, all the usual logarithm properties still apply. Taking this logarithm of both sides gives us this structure to work with. On the left side, we can use the product rule. The log of a product equals the sum of the logs. This splits our left side into the logarithm of our new variable u, plus the logarithm of this exponential tower. Now here's the beautiful part. Logarithms and exponentials with the same base are inverse operations, so they cancel out perfectly. And we get this remarkably clean equation. The logarithm of our new variable u plus an exponential equals a linear term. Now comes the calculus magic. We're going to define a function and use derivatives to understand its behavior completely. Let's rearrange this equation by moving everything to one side so we can think of it as finding where a function equals 0. So let's call this our function, defined for positive values. The roots of this function are exactly the solutions we're looking for. We already suspect that 1 should be a root, since that corresponds to our original guess. Let's double-check this by plugging in 1. Substituting 1 gives us a times 1 minus a to the first power minus the logarithm of 1. Let's simplify each piece. A times 1 is just a to the first power is a, and the log of 1 to any base is always 0. So we have a minus 0. And this simplifies to 0. Perfect. So 1 is indeed a root of our function. Now, to figure out if there are any other roots, we need to understand how this function behaves. Time for some calculus. Remember, the derivative of a logarithm with a general base involves the natural log of that base in the denominator. Taking the derivative of each term gives us our first derivative, a linear term minus an exponential term minus a logarithmic term. And differentiating once more gives us the second derivative. Now here's the crucial observation. Since a is between 0 and 1, its natural logarithm is negative. This makes both terms negative, so the entire second derivative is negative. And when the second derivative is always negative, that tells us the first derivative is strictly decreasing everywhere. Now comes the beautiful finale. We're going to show that our solution is not just a solution, but the only solution. Let's see what happens to our decreasing first derivative as u gets very large. The exponential and logarithmic terms vanish, leaving us with just a. Since our first derivative is decreasing but approaches a positive value, it must always be greater than that positive value. So our first derivative is always positive. Now think about what this means. If the derivative of a function is always positive, then the function itself must be strictly increasing everywhere. And here's the key insight. A strictly increasing function can cross 0 at most once. It's like an elevator that only goes up. It can only pass any given floor once. Since we already found that our function equals 0 at 1, that must be the only root. 1 is our unique solution. Now, let's translate this back to our original variable x. Remember, we defined our original variable x in terms of this exponential relationship. So we get a to the first power, which simplifies to our original guess. What started as an educated guess has now been proven rigorously. This beautiful symmetric equation has exactly one solution. Before we wrap up, I want to show you an alternative way to think about this problem that gives some nice geometric intuition, even though it's harder to solve analytically. We can rearrange our logarithmic equation into this form, where we're looking for intersections between two different functions. Let's see what this looks like graphically. I'll plot both sides as functions using 1/2 as a concrete example. The blue curve represents the left side, and the green curve represents the right side. Wherever these curves intersect, we have a solution. And there it is. They intersect exactly once, right where we expect. While proving this graphically is more challenging, it gives us a nice visual confirmation of what we proved algebraically. So there you have it. What looked like an intimidating symmetric equation turned out to have a beautifully unique solution. The combination of domain analysis, strategic substitution, and calculus gave us a complete understanding of this problem. If you enjoyed this mathematical journey, consider giving this video a like and subscribing for more explorations into the elegant world of mathematics.